The problem remains that I need to learn a variable architecture. So as of now, the assumption it's fully connected. Let me break that assumption over here. So again, let's take a neural network. So that's 2 input. Some hidden layers and output. And this time what I'll do is I won't make all the connections. Here all the connections need to be there, so I don't have an option. And the output Y. So there are connections which are not existing. So let me show the non-existing connections by a different color. So the blues are the ones which are not connected. And the black are the ones which are actually connected. And let me give in the weight values. So this time what I do, I give a weight values to all the existing connections and the non-existing connections. And there will be a bias. So I give the weight values to all the existing and non-existing connections, but then some of them are non-existing, like W1. So I need to tell the system that this, I have given a weight value, but it's not actually existing. So I give a C value to it as well, where C could be zero or one. There is no weight here. So I give it a C value as well, where C is 0 or 1. So first let me, so this is of course the phenotype. I need to make a genotype. I need to make it a genotype of this. So let's try to make a genotype of it. So let's encode the first connection. So the first connection has two things, a W0 and a C0. This denotes the value of the weight. And this denotes if weight is present. The possible values are only 0, 1. Connection does not exist. And connection exists. And I can do it for all of them. So that's W1, C1, W2, C2, W3, C3, W4, C4, and so on. So this time again what I'll do is, first I'll copy all the weights, and then I will remove the connection wherever Ci is 0. So if Ci is 0, I'll break that connection from my library. I'll delete that weight from my library. And then I'll train the neural network. So it's exactly the same thing. So I have a random population like this, pretty much like the last time. So you have W0, C0, W1, C1, and so on. So the first thing is that I need to decide the weight of something. So I'll take this neural network. I will convert this as a genotype into this phenotype, where I will take in all these weights and I will take this weight, put it here, take this weight, put it here, and if this connection is 0, I will actually break those physical connections, and I'll have exactly the same loss function. So my fitness function or my loss function So the ANN that I created, now it's of course I is equal to 1 to number of training data, input for this weights and whether the connection is present or not, yi, plus the regularization parameter. So my regularization parameter is only for the ones for which C was 1, and if C was 0, those are not to be connected. So I say this is Wij times Ci. Okay, I is already used over here. So there are two i's. I better change one to a d. Okay, so that's just renaming I to D. Yeah, so now basically what I say is that, and what I call it as this individual, it's of course a collection of all W0, W1, W2. So let's say for the ith individual, the jth weight value and whether the connection is present or not. So that's C0, C1, C2. So this is the weight value, and this is if connection was present. So it's lambda time. So I only need to consider the weight value if Cij was present. If this wasn't there, then I can say that there's no connection. So the weight value is arbitrary in that case. So it's Wij times Cij. So just take a dot product of these two. So if weight isn't there, if Cij is 0, whatever the weight, it'll become 0. So it's a multiplication of both of them, summation over j. So that's my first regularization. It tries to minimize the weight values, and then I can do another regularization that I want to minimize the number of connections. So lesser the connections, the better the neural network is. It'll avoid overfitting, lesser the number of connections. This is the one that avoids underfitting. So that's a trade-off between the two. So that's my same fitness function. It has, of course, the term taken from the last time, the mean square error, and the same term taken up from last time, that's the regularization. So this is the first regularization. The aim of this regularization is to reduce the values of weights as done previously. So it is to reduce the values of weights and then of course you've got another regularization. So that's another regularization, and the aim is to reduce the number of connections. And once I get this, I can do, so I'll get some fitness value, I'll do ranking, selection. Once I do selection, I can do crossover, mutation. The only thing to deal with is that there are two types of individuals over here. So these are real valued. So you apply a Gaussian mutation, and these are binary numbers, so they are 0 or 1. So mutation is just a bit flip. And similarly for these ones, you can do arithmetic crossover, while for these one, you probably will be doing a scattered crossover because they're just 0 or 1s. So those constraints could be added, and then you make in the new population pool. So that's pretty simply, and that's pretty much straightforward, what we call as the evolution of a neural network, or learning of a neural network based on the genetic algorithm, and it's done on the basis of representing the phenotype neural network by a genotype and then a normal evolution of the neural network. The loss function of a neural network becomes a fitness function.